just try to repeat questions if you can.
Got it. Hopefully I remember.
Yeah. It's not too big of a deal. I think the mic picks up the audience questions, but sometimes it's very quiet. Yeah. Okay, well, welcome back, everyone, to the second talk of the last day of this workshop. So we're very happy to have William He, who is a PhD student from CMU, telling us about certifying any quantum state with few single-qubit measurements. So yeah, take it away.
Nice. Yeah, thanks for having me. Thanks, everybody, for coming. Today, I'll tell you about some joint work with Meghal Gupta from UC Berkeley and Ryan O'Donnell, who's also at CMU. And yeah, this is about how to certify any quantum state using only a few single-qubit measurements. And yeah, feel free to interrupt with questions. OK, so I'll introduce the problem of quantum state certification. To set it up, I have some pure quantum state that I'll call ket psi on n qubits that maybe we'd like to prepare or we think a physical process is preparing. And so I'll call this the target state. And some process, maybe like a quantum computer that you don't trust, is outputting copies of a mixed state. And we want to measure a few copies of this mixed state rho and figure out if it's equal to psi or not. And so I'm going to refer to this rho as the lab state, because we imagine it's prepared in some lab. So if rho has perfect fidelity with psi, then we want our algorithm to always accept. And if the fidelity is at most 1 minus epsilon, then we want to reject with 0.99 probability. Now, because rho is pure, this is like pretty easy. You just measure 1 over epsilon copies in this POVM that contains psi, and accept if and only if all the outcomes are ket psi. So yeah, problem solved. This is like the optimal thing you could do. But maybe let's examine this algorithm. It requires us to make measurements in this basis containing ket psi. And the problem is that performing this measurement is as hard as preparing psi. And for certain states psi, this might require you to make some kind of really complicated quantum computation. And if you can prepare psi, why are you trying to verify a computer that's preparing psi? So we'd like to see if we can use a weaker class of measurements and still certify lab states for psi. And in this talk, I'm going to focus on certification algorithms that only use single-qubit measurements. So you measure each qubit of the lab state with unentangled measurements. Yeah. OK, so I'll tell you some of the question.
You promised that all the copies are the same.
Yeah. So yeah, the question was whether you can assume all the copies are the same, and for this talk, I'll assume they're all the same. So now I'll tell you about the prior work in our results. So previous algorithms for single-qubit certification suffered from one of two issues. Either they only work for a restricted class of states or noise models. For example, stabilizer states, or some examples here. So this is, people have studied this model of certification algorithms. Or they require exponentially many copies to certify any quantum state. And so before our work, it was open whether you could certify any quantum state with just single-qubit measurements. And we answer this question in the positive. We give a copy-efficient algorithm for every state, every target state psi. So this is our theorem. We give an algorithm that takes as input a description of a pure quantum state, n-qubit quantum state psi, makes a linear number of, uses a linear number of copies of the lab state rho, makes quadratically many single-qubit measurements of rho, and satisfies the guarantee on the previous slide. It distinguishes between the case where rho has perfect fidelity with psi or has infidelity at least epsilon. Yeah, question?
So, sorry, this is a very naive question. Maybe you already even addressed it. But these previous results that you listed are for single qubit measurements?
Yes.
Maybe this is obvious, but if you make entangled measurements, what's known?
Oh, like if you can if you can implement like this measurement.
I see. Then your point is you could just do that.
Yeah, you can just do this.
Okay,
Yeah.
I see.
Okay. So yeah, this is.
For example, instead of distinguishing perfect versus perfect, you are distinguishing imperfect up to delta.
Yeah, great question. So the question was basically about the tolerance of the test, whether we require the first case to have perfect fidelity. And the answer is no, we don't require perfect fidelity. We have like a little bit of wiggle room for the yes case. I'll mention this later because like when I talk about the algorithm, I want to focus on the case where there's perfect fidelity.
Is there a matching lower bound? Like classical shadows gives you something which is like incomparable to this?
Oh, you mean this if this is tight?
Yeah.
That's okay. So the question was whether you need a linear number of copies, and the answer is I don't know, and that's one of the problems that I'll pose at that. Okay, so this theorem is about this is our main theorem, and it follows from the following single copy algorithm. So we give an algorithm that takes as input a same description of cat psi, and now it takes a single copy of the lab state rho, makes n total single qubit measurements to rho, and certifies if rho is equal to cat psi or not, but like with worse probability. And so now I'm gonna tell you about how to prove this theorem. Yeah.
Are you gonna tell us like what this description?
So maybe later, but yeah. So the question was what this full description, like how it's quite complicated. To start, let's just assume that we have exponential or infinite time, and we're given a full description of this cat psi, and we don't care about running time. And I'm not gonna. We can talk about that later. Yeah.
But like, does your algorithm end up? Is it actually efficient in?
Yeah. So the algorithm is efficient given a specific type of oracle access to this cat psi, but you need to instantiate this oracle access and to instantiate the algorithm. I won't get to that in the talk, but yeah, you can do it.
If you have a description and you know the gates used, can't you just reverse that and apply that to rho and then like?
Yes. So the question is whether you could like take this description of psi as a circuit description of it, and just like apply the inverse to rho. The problem is that circuit might be like really long. Yeah.
But does that prove the theorem or?
I mean that goes back to Sean's question. Like if you have that circuit, then you can implement this POVM that I was talking about, the optimal POVM where you measure the basis like containing psi. And that's like.
I guess maybe my question is the algorithm I said the algorithm in the theorem, or is it a different?
No, not the same algorithm. Yeah, because that's not a single qubit measurement.
Well, if you start from the computation, like an all zero state, and then it's a state preparation thing for psi, then you should end back up in an all zero state.
Yeah, but applying like a circuit and then applying the measurement.
Oh, okay, sure, yeah.
There won't be single qubit, right?
Okay, so there's really nothing else to do except to like prove this theorem. So I'll do it. I'll now describe our algorithm. And without loss of generality, I'm going to focus on the case where rho is a pure state. And this is because this algorithm takes a single copy at a time, it's going to generalize to the mixed state case pretty easily by like linearity of expectation. So now recall that we want to distinguish between the following two cases: perfect fidelity and infidelity at least epsilon. Okay, I'm nothing new here. I'm just recalling this. Okay, so I'll describe the algorithm. The algorithm has the following general structure. You don't have to follow like everything, but it has the following general structure. We're going to first choose a index k in 1 through n uniformly at random. We're going to measure the first k minus 1 qubits of the lab state in the computational basis to get some length k minus 1 string and a corresponding reduced state, which is lab conditioned on this k minus 1 bit string. Okay? And then we're going to do some stuff. Okay, I'll get to like what this stuff is, but intuitively it's going to be checking something about the relationship between this like lab condition on x with another, if you measured the kth qubit and got a 0, and then the corresponding case where you got 1 on the next thing. You're doing something like this. And you know, if you want a picture, you can try to draw this pure state lab on a complete depth n binary tree. In this case, I have a tree of height 3. And what this first 2 steps is doing is we're going to like measure the first k minus 1 qubits of the lab state, and we're going to end up at some internal node in the tree x. Okay? And this purple stuff is just going to be like checking something about the states that are on these 2 subtrees. Okay? That's like the general structure you should have in your mind. Okay, I'll pause for questions. I haven't said anything, so maybe not the right time to pause. Okay, so yeah, recall this tree. We have this tree. I just put this so you can look at it. What we're going to do is we're going to like formalize what I just said in the outline by decomposing the infidelity between psi and lab into contributions from each internal node in this tree. Okay? So like I'm going to blame each internal node for some part of this infidelity. Okay, so for a particular internal node x, I want you to like have this decomposition in mind. We're going to write the target state with these u's, and the purple is like the left subtree, and the brown is the right subtree, and the corresponding case for labs has these. So I'll take 15 seconds to internalize this. And no here u and v don't have to be unit vectors, or yeah, they in general won't be.
Sorry, what is psi of x again?
Psi of x is like the target state post-selected on getting x in the first computational basis measurements.
Oh, okay, and lab is what you measured.
Yeah, lab is what you measured. Yeah, this is the target state, and then the state you want to certify.
So psi of x is a state, is norm 1?
Yes, yes. All the cats will be norm 1, and then like these things might not be norm 1, so I didn't make them cats. Okay, cool. And okay, so this is the blame, the error that the contribution from x to the infidelity. It's going to be this quantity. And before you like stare at it for a little bit, like maybe you can check if lab were really equal to the target state psi, then this is truly 0. And in some sense, like this is measuring the like phase difference between these 2 trees. You can sort of have this intuition. I'll have an example later, but I'll take another 15 seconds here.
So is it clear that when the error is 0, the 2 states are equal?
Like you would know that. No, that's not necessarily true.
Or like even psi x and lab x could be. Like if error x is 0, does it mean that psi x and lab x are equal, or that's not true?
That's not true. You need that to hold for like all x. This is only the blame on a single internal node.
Okay.
Yeah. Question.
So computing this psi x post-selected on a large number of measurements could be exponentially hard computationally, right?
Yeah, so the question was about computing the hardness of computing the psi x when you're actually executing this algorithm and you need to compute this. That's a good point, but you have to like make some leeway because these states have exponentially large descriptions. So like for us, we're just going to pretend like we're going to have an oracle that gives us information about this state.
Yeah. So this is correct. This thing, if you sum it over x, then it gives you the total infidelity. And could you explain this expression, like why exactly?
I'll do that on the next slide. I don't have the computation here. It's like some algebra, but it follows from the case where n equals 2. And you
What
can
follows this? The sum is infidelity, or?
the sum is infidelity. Yeah. So it's a computation that you can do, but
So you someone almost like guess the expression and it happens to work.
I think this was like we had some motivation for studying this.
But
Question?
Can you say one more time what U0, 1 are like as
Oh, good. Okay, so it's just what the states that you get when you like post select on 0 and post select on 1 in the target state case.
Yeah, the penultimate equation, you haven't done anything. You just wrote a very general expression, right?
Yeah,
For
yeah.
these.
I haven't done any like actual math. I'm just decomposed this. Yeah.
And then what is the relationship between epsilon and error x? Like,
I'll show you on the next slide. Yeah. There's. I can even tell you like if you sum over the x of the errors in a certain way, then you get the infidelity. Okay. Great. I'll move on to the next slide. Okay, so yeah, drew the tree again. And at each internal node, we're like putting some blame on it. So this is the error at the string 1, which corresponds to that internal node. And like this is the error at 1, 1. And here's a lemma. This answers your question. If you take the expectation over x of this error, then you get exactly infidelity over n. This is something that you can prove, as I said, in the n equals 2 case, and will follow by induction in the general case. And note this expectation is over the following experiment for drawing x. You choose k uniformly at random, and you measure the first k minus 1 qubits of lab in the computational basis. So this is exactly, if you recall the algorithm, overall algorithm outline, this is like exactly what you get by executing steps 1 and 2 in the algorithm. Yeah.
Wait, sorry, can we just go back to the previous slide for a second?
Hmm?
I'm just confused. Okay, so here, like, suppose that the way that psi x and lab x differ is like, I would say U0, U1, V0, V1 will have the same norm. So they're all like norm, I don't know, 1 over 2.
Sure.
And then it's just like V0 is just like U0 rotated a little bit in some direction, and like V1 is like U1 rotated in the same direction. It's like that error could be 0 potentially, right? Because like the dot product of U0 with V0 could be exactly equal to the dot product of U1 with V1.
At that node. And then
So
it'll be picked up on the...
It'll be picked up on the next. Okay, that's what I wanted to check. So basically, this is sort of like. This is only kind of like an error contributes to x, like if you have the norms wrong at level x or something like I'm just.
And the phases.
And the phase. Oh.
Yeah, it captures things about the phases.
Oh. Okay.
Yeah.
Oh, okay. That
Question?
makes more sense. Yeah.
I'm confused also, what is this labx wave function?
LabX is like if you measure the lab state in the first k qubits and you got x, then this is like the resulting reduced state that you got. This is like the post-selected state.
But you don't have in your hand this entire thing, right? You got one result. Not
No. Yeah, I'm not saying anything. The algorithm's not doing any of this. Yeah.
This is just a quantity in your
Yeah,
analysis.
this is just, I'm just doing math. There's no algorithmic stuff happening right now. Yeah.
The display 0 and 1 are k plus first.
Oh, sorry, what's the question?
Is display this tensor factor is 0 and cat 1. They are k plus first qubit or k?
This is this is the k plus first qubit now. Maybe I should have put k minus 1 and this would be the k qubit now. Okay. Sorry about that. Okay, so yeah, we have this lemma, which tells us that the average error of x that we see in the first two steps of the algorithm overview is going to be like exactly related to the infidelity. Okay, so this like gives us a plan to design a certification algorithm. We want to design a complete test, so it always accepts the target state. We don't want to like come up with a test that just always rejects. Yeah, and we want to reject any lab sub x, like we measured k minus 1 qubits and we got lab sub x, and we want to reject this reduced state with probably at least this error. Okay, and then we would have a full algorithm because, well, okay, completeness follows because I didn't design some nonsense test. And soundness follows because of the following sequence of inequalities. So the probability of rejection is just the expectation over x of the probability of rejection that you landed at x after your first k minus 1 qubit measurements. This greater than or equal to is like the assumption given here. And this last thing, this is like this green lemma that was on the previous slide.
Okay, so just to check, like the expectation over x, that's over the distribution of x's you get from measuring lab.
Yes,
okay.
yes.
Yeah. So, I mean, how do you make it infidelity? Because there's this factor of 1 over n, right?
So the question is where this 1 over n comes from, essentially?
Yeah,
and
so if you measure like the first n minus 1 qubits, do you still get a nice expression? Or, like, if you fix that,
fix k equals n minus 1. Such an algorithm can't work because you can't detect phases at like the higher levels of the tree. And in fact, the randomization over k is exactly why you get this 1 over n factor.
No, but in the soundness case, you also want to reject with probability epsilon, like infidelity, right? So
yeah, so I'm going to design a test that rejects with this probability, epsilon over n, and I'm going to repeat. So that's actually where the linear sample complexity comes from. Okay. Cool. So let's design this test then. So let's gain some intuition with this example. So I'm just recalling the.
Your cable come loose.
Let's try it. Oh dear.
Oh, that looks better.
Maybe I have to do this. Okay. Okay, yeah, so we want to, I'm just recalling the goal here. We're trying to design a test that, like, for this internal node in the tree, once we get to this internal node, we want to reject with probably at least this, with a non-nonsense test, like a complete test. So let's do the example where the internal node we're at is actually just the root. Like we chose k equals 1. And the state we're trying to test is I think it's called APR pair. And yeah, like let's suppose that the possible error is that we have a phase error. So instead of a plus, we have a minus here. And we want to somehow like pick this minus up. And note that in this case, if lab is actually equal to this, then the error at this root node is equal to 1. And in fact, this is like the only error that's in this, like the only node with any blame on it, right? Okay. A question?
I thought lab x was n minus k qubits. Or x is a k length k string.
This is empty string.
Oh, yeah, I'm just saying at the very top, you say n minus k plus 1. I thought x is length k.
No, x is length k minus 1. Sorry, there's an off by 1 on like one of the slides. So yeah. Like we're doing the kth level. Sorry about that. Okay. Maybe I'll pause for like 10 seconds again. Okay, yeah. So how do we detect this minus error? Well, here's an idea. Let's like measure the second qubit to try to get this phase to somehow show up on the first qubit. Right? So we're going to measure the second qubit, and so like in the reduced state on the first qubit, we want this minus sign to like show up. And let's try like a, I don't know, idea. Let's try maybe measuring the second qubit in the computational basis. Well, this is a terrible idea actually, because like if you get an outcome of 0, then the first qubit's in state cat 0, and yeah, same thing with 1, and this is regardless of whether a phase error exists. Like you completely destroyed information about the phase by doing this. Oh dear. Yeah, okay, so what do we do? Well, let's know what was the problem with like measuring the second qubit in the computational basis? Well, the problem was that like by measuring this in the computational basis, we completely destroyed one of these purple or brown components. So like, how could we possibly detect the phase? We just completely just killed it.
When you say like killed it, it's really you killed the superposition between the two components, right?
Yeah.
So you may kill the component. Okay.
Yeah. Right, so let's try again. And we're going to be a little smarter this time, so we're going to measure in the Hadamard basis. We're going to measure the second qubit in the Hadamard basis. And now what happens? Well, if we got an outcome of 1, a plus, if there was no phase error, then we would have a plus on the first state. But if there was a phase error, like this minus, then we would have a minus on the first qubit. And we'd be able to detect this, and like the symmetric thing happens with the cat minus state outcome. And like, okay, so I want to like impart some intuition that the reason this was good was that the Hadamard basis was fair towards cat 0 and cat 1. It was like, these two states are both phase states in this Hadamard basis. Okay, so I'll pause again for questions. Okay, then if there are no questions, then I'll end the example and declare that we've acquired some intuition. Okay, so let's go back to like the general case. I'm just recalling notation here for your convenience, but yeah, you can ignore this if you want. Okay, so let T be some basis for like the last n minus k qubits, in which case like these are like scalar multiples of states on these qubits, in which like both U0 and U1 are phase states. So like we can imagine like U0 is just the all ones vector, normalized of course, and U1 is like a vector of phases, normalized of course. And I'm not going to worry about like how we're going to measure in T yet. I'm just going to pretend like it exists, that we can like do it with the single qubit measurement model. Like, let's just pretend it exists. Okay. Okay, so the next two slides are like a bit of algebra, but maybe, or like okay, there's 2 short slides of some computations. If you don't follow them, it's fine. Like, hopefully the intuition is already there. But basically, if you measure in this basis T and you get an outcome, sorry. I'm going to propose the following algorithm. I'm going to first measure the last n minus k qubits in this like special basis in which magically U0 and U1 are phase states. Okay, I'm going to compute the reduced state if lab had been the target state on the kth qubit. So this is going to be a single qubit state psi prime. And I'm just going to make the optimal measurement on this kth qubit. So this like psi prime per basis, and I'm going to only accept if you give me what I expect. That's the algorithm. And note that if I got, this B should be T, sorry. If I got an outcome L on the last n minus k qubits, then the reduced states psi prime would look like this, and in the lab case it would look like this. And so, you do some math, and the acceptance probability is this. Note that this like normalization 1 over PL. PL is with respect to measuring a lab state in this T basis and getting, this is like the probability of getting L under the lab state. And then, okay, so this is like conditioned on L. If you multiply by P sub L and sum over all the L's, you get that you get the you do the computation and you get that the rejection probability is equal to this. So okay, so there's some like 3 lines of math going on in the middle. But the rejection probability is going to be like, I flip this plus to a minus, basically. Okay, and then you do a computation, and okay, so the error sub x looks like similar to this. You have to do some things with the phases, but the end result is that the probability of rejection given x is at least error sub x if you do this computation in full. So yeah, question?
Can you go back to the algorithm? Yep. Okay. Thank you.
Yeah, so as warned, like it was sort of just like some computation. You use like this step, for example, is Cauchy-Schwarz, and
Can you go back to the algorithm?
oh, sorry. Yeah.
Okay, I have a question. Let's say the target state was just a phase state to begin with. Then
Yes.
is the algorithm just saying, I'll just measure everything except one qubit, and this one qubit is also a phase state. The target state, this reduced state, is also a phase state, and I'll just measure, are you this guy or you're orthogonal to this guy?
Yeah. In fact, you just proposed the algorithm designed by Juan Preskel Soleimanafar, this HPS algorithm. And you can show that in the phase state case is actually like a realization of this algorithm, so it's sort of a special case. And you can show that this has like the same guarantee that we give.
So the tricky bit is like, not every state is a phase state.
Yes.
And you got to show that there's some basis in which it is. Is this T, or like?
Something similar to that, but like note that we use the computational basis to begin with. Like that, we're not putting it fully into a phase state, but we're putting like subtrees into phase states simultaneously. Yeah.
How do you find T?
How do you find T? Oh, I pretend like I have it. I'll tell you how to find it later. Another question.
This is, I guess, similar to Robin's question, but I guess there exists this T. You know that.
There exists this T, and moreover, I'm going to show you how to measure in it, but I just haven't gotten there yet. Yeah. Yes?
This might be a completely silly question, but like, are you secretly doing swap tests in brute force?
I think. Okay, so the question was whether this is just like some version of the swap test.
Then it's like online swap test somehow, and you implement the other states classically.
Maybe I think the analysis looks somewhat similar to the swap test. Maybe.
Okay.
I'm not too sure. I'm not too familiar with swap test, but yeah, maybe we can talk about it. Okay. I'm gonna go back after. Okay, so you do some computation and you like yeah. Maybe the intuition was like the real, like nothing really happened here. It's just some computation. Okay. So we're done, right? Like I told you that once we have this, we're done. So we have this, and now we're done. Modulo this fact that we don't know how to measure, or I haven't told you yet how to measure in this like special T basis in which both these states are phase states. So how do we get this basis, and how do we measure in it? I'll note here that this is the idea of how to do this has appeared in previous work. But it's like fairly simple, so I'll just like, I'll go through it. So yeah, we need a basis T in which both U0 and U1 are phase states, and U0 and U1 now are just like arbitrary single qubit states. Sorry, they're arbitrary states, and for the simple case, I'm going to start with the case that they're just one qubit states. Or normalized, they're not normalized, but yeah. So I'm going to put them on, so to design the basis, I'm going to draw them on the block sphere. So I have like U0 going this way, U1 going this way. And I'll just measure in this perpendicular basis to both of them. And this gives me this will give me that U0 and U1 are both phase states in this basis. So I'm done in this like special case of one qubit states. And moreover, like this was clearly a single qubit measurement. So yeah, I'm done. So then let's handle the general case in which they're m, which is equal to n minus k qubit states. This is the general case. So I need to design this basis T. It's not clear yet if it exists, but I also need a stronger property that I need to be able to implement this T, measurement in T, using only single qubit measurements. So I need this to be some kind of special, not just any old basis, but some kind of special basis with special structure. But the thing I'm going to try is induction. So the first thing I'll do is I'll compute the reduced states of U0 and U1 on the first qubit. I'll get a basis that gives a 50-50 outcome on the first qubit. And then I'll induct using classical adaptivity. So this is going to give me two possible reduced states, and I'll just induct and get the bases for those, and this is going to give me like an overall, like a decision tree basis is what we call it. So yeah, for this first step, now instead of having vectors on this block sphere, you have vectors potentially inside the block sphere, but you can do the same like perpendicular thing. And yeah, question?
Sorry, do we know U0 and U1?
Yeah, so this is algorithmic. This part is algorithmic, and we're going to have like an oracle that gives us U0 and U1, or at least like the single qubit reduced states. So this is like part of the, like you're asking about a computational.
Well, I guess this algorithm that you're saying, is it assuming we know U0 and U1 or no?
Yes, it is.
Okay, yeah, and then so then my question is, we're assuming.
You remember U's correspond to the target state, and you have a description of this target state. The V's are the ones that correspond to the lab state.
Oh.
Yeah. Okay. Oh, another question.
Apologies if this is a dumb question, but if your descriptions of let's say your description of your state was small to begin with, because it was sparse, does this computation, is it efficient in the description size in general?
The question is whether if you have a sparse description of this target state, then you can have a fast algorithm for it. I mean, okay, you need the description to like allow you to compute these reduced states, basically. So it depends on like what you mean by like efficient representation. Yeah. Okay.
I'm maybe slightly confused by the induction. So the inducting, the thing you're calling is like, now these things are mixed states, right? There are different types of objects from U0 and U1. Like.
Oh no. So I start with two pure states.
Yeah.
I compute the reduced density, the reduced states on, these are mixed states on the first qubits.
Oh, okay.
And then I measure the first qubit in this green basis.
Yeah.
And then I induct on the corresponding pure states, because now I've post-selected on like the green basis outcome.
Oh, okay.
Yeah.
And there's no, do you have to do it for like both possible green basis outcomes or something, or?
Yeah. So this is, it requires adaptivity. So yeah, you measure the first qubit, you look at which green basis outcome you got, you compute the reduced state and induct. You go back to step one. Another question?
Maybe just rephrasing what you said. So this basis T is not merely a function of U0 and U1, but it's also a function of the measurement outcomes that you get as you keep making this basis.
Yes. So the question / comment was that this T depends on the outcomes of the previous measurements, right?
Even the measurements of the remaining qubits, not just the first k qubits. We measure the first k qubits. That's all fine. But like even these n minus k qubit state that you have, you keep measuring it qubit by qubit.
Yeah.
This basis T keeps forming in your mind as you learn new measurement outcomes.
Yes, this is true. So this is where the classical adaptivity comes in. Yeah. Okay. Any more questions? If not, then I'll you'll measure the first qubit in its basis and you'll induct. Okay, so that now actually like completes the proof. But just to recap, let me give you the overall algorithm that I censored before. Okay, so again, we're going to choose k uniformly at random. We're going to measure the first k minus 1 qubits of the lab state in this computational basis to get a length k minus 1 string. We're going to let T be this like special decision tree basis in which both the post-selected states are phase states. We're going to measure the last n minus k qubits of T, ignoring the kth qubit so far. Right now, after step 4, like the kth qubit is unmeasured. Everything else has been measured now. We get some outcome L. We compute the reduced state on the kth qubit that the target state would have been in if conditioned on these measurement outcomes. And then you measure the kth qubit of the lab state in this optimal basis, and you accept if and only if you got the outcome that you expected.
So just like maybe reiterate like Robin's question, like steps 3 and 4 are really not, they're not done like as written, right? It's not like you just do step 3, get the whole basis, and then measure. It's like you're really kind of doing 1 qubit at a time out of the last n minus k qubits, right?
Yes, so,
okay.
Or the comment was that, I think that, yeah, like these,
like I'm just saying you haven't written the adaptivity in steps 3 and 4.
Yeah, I haven't, the step 3 actually has is a loop, over the single n minus k last qubits. Yeah.
Do you think the step 1 and 2 are necessary?
Okay, so the question is whether I think steps 1 and 2 are necessary. In what sense?
It could ease your analysis, but maybe 3 and 4, starting with the very first qubit, could be sufficient.
Oh, okay. So the question is whether you can just set k equal to 1. This doesn't work because of something Anand brought up, that you can have, okay, you remember this like error sub x is like this inner product between, like that quantity could be 0 even if the u's and v's didn't match. Yes. Okay. Cool. Okay, so that's the overall algorithm, the final analysis. I'm just going to reiterate, like, completeness is clear. Soundness is this sequence of inequalities that I mentioned. And okay, that completes the analysis, but we can actually get something stronger. Umesh asked about this earlier. We can actually get a slightly tolerant tester in that the rejection probability is not only lower bounded by the infidelity divided by n, but upper bounded by the infidelity. And the corollary is that we have this like slightly tolerant tester that distinguishes between epsilon over n infidelity and epsilon fidelity. That's the, yeah, this is just by repetition and thresholding on how many acceptances you got. Okay, so I'll mention a few open problems, or I guess people have already mentioned these, but first the test is like very slightly tolerant, 1 over n tolerant, in that you can distinguish between epsilon over n and epsilon infidelities. The natural open question is whether you can turn this into a constant tolerant test. I think this is quite important for like quantum. Here, quantum computers are noisy. Yeah. And the second one is, okay, so this test for constant epsilon at least needs a linear number of copies. I don't know of any good reason why constant number of copies shouldn't be possible. And note that like the constant number of copies is possible if you allow arbitrary non-single qubit measurements. So this would be like super cool, I think, if you could simulate arbitrary measurements with just single qubit measurements. Before concluding, the question.
Doesn't it violate a lower bound on testing stabilizer states if you only have access to single measurement? Single quantum measurements. There's a lower bound on square root of n.
Oh. So the comment was that there's a lower bound for single qubit measurements already.
Yeah.
And okay, so okay, so then this would be already answered, I guess. Okay. Yeah, but I don't. Yeah, I'm not aware of this.
So I can share the pic.
Yeah. Okay. Before I conclude, I just want to mention one last point. So 2 more slides. We can view our algorithm as the power of illustrating the power of adaptivity in these like certification and testing algorithms. In that, okay, so note that this decision tree basis thing was extremely adaptive. And it turns out that this is necessary. And what I mean by this is that we show a lower bound against adversaries that make non-adaptive single-qubit measurements. So for every copy, they fix the single-qubit measurements they're going to make on every single qubit beforehand, and they just do it. They just make all the measurements in parallel, say. In particular, we show that there exists a particular n-qubit pure state such that any algorithm measuring copies of row in this product basis, which is non-adaptive algorithm, needs an exponential number of copies of the lab state to certify. Okay. Okay, so this paper is on the archive. V1's on the archive. V2 will be on the archive very soon, and it includes the lower bound and some improved writing. If you would like to access it before it gets on the archive, which will be very soon, you can scan this QR code. It's posted on my website, also listed here, if you're interested. And that's it. Thank you.
Okay, so thanks, William, for a great talk. I will we'll have some time for questions, and I'll pass out the mic. But first, I will ask my own question. So my question is, you mentioned at the beginning sort of this comment that if you could just synthesize the state yourself, then why are you even bothering to certify copies from some other source? Is it conceivable that you could have a state that you cannot synthesize, but you do have Oracle access to in whatever means you need to implement this algorithm? I guess it's a question about how powerful the description is, really.
Yeah, so the precise, the type of description or Oracle access that you need is you need to be able to compute reduced states on single qubits of any post-selected on product, a sequence of product measurements of the state. And I think other people might know better than me if this is a very realistic Oracle access model. But you do need some kind of Oracle access model because these states have exponentially large descriptions. Mm-hmm. And yeah. Does that answer the question?
I think so. Well, maybe my question is more if you had this Oracle access model, let's say you had this Oracle access model and you were allowed entangled measurements, could you then just do the direct measurement onto the basis of psi? Would this Oracle let you implement that measurement?
Oh, like this, the PO, the optimal PO.
Yeah, exactly. Yeah.
I'm not sure. Yeah, I don't know.
Cool, thanks. Okay. I'll bring the mic to you.
Even if you have a polynomial length description of your state, is it obvious that the post-selected thing has or it's not obvious to me that post-selecting on these measurements would have a polynomial length description because there's potentially exponentially many of the U-naught that you would have to compute, but maybe I'm also didn't understand.
Oh, I guess it depends on what you mean by polynomial length description. If you have some polynomial length descriptions are more useful than others for computing these reduced states. So it really depends on what kind of description you have.
Yeah, that makes sense. What's an example of a polynomial length description that would also easily allow you to get the U-naughts?
Can you go back to the uncensored algorithm? Yeah, maybe I'm not understanding something correctly, but I'm a little scared by step 2 because you've fixed to the computational basis. So, for example, the UPR or the CAT state or the GHZ state, wouldn't measuring in the computational basis to begin with?
You might not measure. You might pick k equals 1 and not. You're worried about the phase, detecting the phase error. Yeah. So you might not. You might pick k equals 1 and then you'll be fine.
Thanks.
Is it easy to describe the counterexample for the lower bound?
It's easy to describe within 5 minutes, but I'm not sure we have time.
Anyone else? Oh, yeah.
So you said we could also view this as like the power of adaptivity for state certification. Do we understand, maybe not necessarily from your work, but do we understand what states can be certified without adaptivity? Like, is there like an understanding of this?
Okay, so I like this HPS algorithm can be made non-adaptive. Like if I first describe you the algorithm, it's like it's almost non-adaptive in that you measure like n-1 random qubits and you make the optimal measurement on the last one. So you make n-1 non-adaptive measurements, and then you do adaptivity on the last one. And I think using some like classical shadows or something, you can make this non-adaptive. And like this works for a class of states. I think. Okay, that's like one example, I guess. But yeah, there's probably other examples of non-adaptively certifiable states.
Maybe a follow-up question on the same theme. Do you think you need this amount of adaptivity? Because you use like maybe order n amount of adaptivity, right? Do you think your protocol could get by with less, or maybe some other protocol? I don't know.
So I don't think so. Or okay, maybe you could like reduce. Okay, I don't know of any good reason why you wouldn't be able to reduce it to like, I don't know, n/2, but I know you can't reduce it like all the way down to like little of n or something. This is
like your lower bound proves that.
Yes.
This might be a difficult question, but I guess so like one approach for doing this whole thing is to do classical shadows, and then I guess you get like 1/epsilon² scaling, and maybe if you can compute k designs, then you can do this. So maybe like if I can apply like a log depth circuit to my my state before measuring, then this would work. What about constant depth circuits? Like instead of like a product state, can you apply some like very shallow circuit? Could that ever possibly help you?
Let's see. You could like would a constant depth circuit like basically turn qubits into qdits of constant d?
Not necessarily.
Okay. Okay, then I'm not sure how. Yeah, you're asking if you can like massage the state into a nicer state using a small.
Well, just like you're giving yourself, instead of product measurements, give yourself like slightly more powerful measurements.
Yeah.
But not, I guess, not too powerful so that you can just use classical shadows.
Yeah,
something intermediate. Yeah.
Yeah, that's a good question. I'm not sure.
What happens if I run this algorithm on a noisy quantum computer?
Sorry, like the.
If there is a like small amount of noise, in my measurements, for instance.
Oh, okay. I think.
Basically, a rephrasing of some of the other questions, which is like, are you able to tolerate a little bit of error on the preparations of your state? Like, say they're all epsilon close to like all the copies of the lab state are not the same, but they're epsilon close to some.
Oh, okay.
Psi lab prime.
Yeah. So I guess the question was whether you really need rho to be identical across the copies, and this is not the case because our test. Okay, I said you could assume this beforehand, but now you may see like our test works copy by copy, so we need them to be like on far on average. Thanks.
Okay, maybe we can take one last question. If not, then let's thank William again, and we will see you back here at 2 p.m. And there's one more talk, and then there'll be lightning talks afterwards. So I think that's the schedule.